remember. How are you? Okay. I think you're doing a little behind the sun.
And I'm trying to do the homework for this week and all. I think I need a few more.
That's. But a lot of people.
I think that's close enough. Well, welcome back, everyone. Looks like it's time to get started. We're nearly done with the third week, so that's pretty cool. After 1 week from today, we're 25% done with the entire semester. That's kind of shocking in a way. It kind of feels like it's moving fast. But for the moment where we're at in the course, we have our first quiz that's due today, and the new quiz has been posted. Pretty much this is going to be the pattern every week, excluding, say, for example, potentially a week where we have an exam. I feel like that could be just too much going on in one particular week. We'll probably still assign a quiz on this week, but think of that as just an extra opportunity to study for the exam, since all the quizzes that you'll see posted make excellent exam questions in their own right. So with where we're at so far, we're just about done with section 2.5. Let me get it where it should have been. There we go. After we finish that off, we're doing chapter 3, and chapter 3 is going to be pretty short in this course. We're not going to cover every topic. In the readings, I always try to indicate what's covered and what's skipped. Sections 3.3, 3.4, very, very interesting, but we're not going to directly cover those sections. Our course in statistics doesn't really use that type of data you would see in those sections. So we'll just be focusing on 3.1 and 3.2. So just one homework assignment relative to chapter 3. It's about the size of these original sections up here in chapter 2. Well, any questions so far, folks, with where we're at? Okay, other thing I should mention is, because this is our first quiz, the way you can hand in your quiz is, well, maybe I should start, how do you even open the quiz? Just as a refresher, click on right here, the quiz 1 link. Same for quiz 2 to see your second quiz. Click on that again to open the PDF if you clicked on it the way I did. And you don't have to print these out unless you'd like to. It looks nicer if you print them out, but you're totally welcome to just use ordinary notebook paper. That's completely fine with me. And if people are working on these digitally, say on an iPad or some other kind of tablet computer, just convert your file to a PDF and send me that file, and that'd be just fine as well. If you're not sure how to convert to a PDF, just send the file. I can probably reverse engineer it, but there's certain file types on the iOS platform that I can't open too easily, like dot pages or things like that, are a little bit difficult on my machines. But if you're not sure how to convert to a PDF, just send it over and we'll get it figured out. The due dates, again, these are more for pacing than anything else. So if you didn't quite get it done up the first quiz by this day, I still would accept it if you get it done at some point. So this is really just your opportunity to practice. How does a statistic problem from my stats lab transfer onto paper? That way, when you go to take exam 1, it doesn't feel just totally different from doing my stats lab problems and then going to a paper problems like these ones here. So that's the major purpose of the quizzes. And again, that's our second one now posted. Let's just take a look at it because I forgot what the problem was I assigned. I don't know if I should admit that, but I did forget. Okay, so here's our quiz 2. Looks like we have several pieces of data. They say it is, I'm not sure where it says, but somewhere it says how many observations are here, I think. And they give us a histogram relative to that data. All we want to do in this problem is describe the shape of that histogram and then calculate some basic statistics, the sample mean, sample standard deviation. So this one's more of a calculator style kind of quiz, but this one is pretty critical because when we go to take our exams, you will have to use your calculator to compute these things, the sample mean, sample standard deviation. You could do this one by hand, but this one is terrible to do by hand. I'll never ask you to do that on a real exam. You really need a calculator to do that computation in a reasonable amount of time. So that's our second quiz. Any questions or comments at the moment? Okay, I think that's just about the end of my announcements, but one more thing. As I get closer to completing the grading this weekend, probably Friday or Saturday, I'm going to start filling out more details here about the coverage on exam 1, as well as related documents for study guides and those kinds of things, sample exam problems. So there'll be more information posted here later on over the weekend. Well, this is where we left off then. We are in section 2.5. And this problem right here doesn't seem like it's the funnest one. We have a random sample, 4 pieces of data, and we're going to calculate the sample mean, sample variance, sample standard deviation by hand. Now, why would we do that when we have a calculator right here? Well, the reason for all that is, if you really look at the formulas for sample mean, sample variance, sample standard deviation, let's in fact take a look at them. Here's sample variance and sample standard deviation. It just feels like there's a lot going on. And these are formulas we use more often than the median and interquartile range. So I figured, just to understand the formula better, let's actually do this by scratch. Again, this will never be an exam problem. It could potentially be a quiz problem, but I think it's more just something we're doing now to practice understanding the formulas is the bigger takeaway in this problem.
You want to do it by hand?
Yeah, we're going to give this a try by hand, but we'll also try in the calculator too, as a check on our answers, see how accurate we actually got. Because we're rounding intermediate computations to 3 decimal places, our final answer to 1 decimal place, we may not be as accurate, as fully accurate as the real calculator. But let's get started. It says, calculate the sample mean, variance, and sample standard deviation by completing the following table. So our goal is to fill out everything on this table. And the first column is kind of mysterious. It just says yi. By the way, the red is because I printed xi when it should have been y's using our textbook. Yi is just referring to the data, so it's referring to these values right here. For example, you could call this y1, y2, y3, and y4. In fact, let's add that detail there. So here's y1, y2 refers to data point 15, and so on for y3, y4. So this column is pretty fast to fill out. When it says yi, we're thinking y1 first, which is 13, y2 next, which is 15, and so on. So 13, 15, 19, and 21. We might as well start color coding this. In this position, we're about ready to calculate the sample mean. But to do that, we would also want to take a total. Awesome. So you like symbols, it would look like this. Sigma yi. You're just adding these all together in the calculator. So we're still using the calculator, really. We're not doing everything by hand. And you said it was what value again? Sorry? 68. Gotcha. So what I said here is summation yi. In other words, add all this stuff up, you get a value of 68, which means
Sum of all the y.
exactly. So it means we're pretty much have the mean, right? We go y bar equals, take the 68, and what would you do to the 68 to get that sample mean finally? Absolutely. If there's 4 pieces of data, observe the 4 right here, or just that there's 4 pieces of data, that means you're dividing by that 4 specifically. So 68 fourths, 6/8, division key is way over here by the up arrow, gives us a nice even number, 17. So the numbers start off kind of friendly, then they start to lose their way in a certain sense once we start to look at the rest of the table. But does that make sense to folks on how we got the sample mean? Okay, notice there's a lot to tie together. There's the word sample mean, but then there's also the symbol y bar, and there's also the formula, take the summation and divide by 4. So it's a lot to tie together in our minds. And again, we use these formulas so often. The purpose of example 2 is just to make that correspondence, get used to seeing those things coming together. So in the spirit of that, let's call this the sample mean, just to be specific. Now, this is called deviations for the mean. What we're doing here is we're measuring the distance of every observation from its sample mean. So the way we do this table here is we take a data value 13, subtract the sample mean, which was 17, and perform the computation. So 13 minus 17 will give us a -4 to start. Then go down the line, every data value, just subtract the mean. So next, 15 minus 17 for a value of -2. 19 minus 17 for a value of +2 now. And last, 21 minus 17 for a value of +4. So those are the deviations for the mean. Now, if we add all these up, we would say summation, just to say add them all up. What we're adding is yi minus y bar. And in this problem, adding those all up gives you 0. This is not a coincidence. It turns out every single time you gather data like these, calculate the sample mean, subtract the mean from every data value like we just did, it always totals 0. So this is like a check in the middle that our numbers are actually working as intended. So as a check, this must is always a strong word, be 0. If you did any rounding, however, it might just be approximately 0, which is good indication you're still in great track. We didn't do any rounding whatsoever, so we expect exactly 0. Well, any questions, folks, to that stage in column 2? Okay, the deviations for the mean are important, but they're not what actually gives us the sample variance. Variance is supposed to measure how spread out the data is, and every time you do this, you get 0. That's not giving us any indication whatsoever with the spread of the data. So let's pause right here and take a look at the formula. The next part of the formula is saying, if you want to calculate variance, you need this. Bring it down below. Okay, so to get the variance, we do essentially just what we did right here. You subtract y1 from y bar, but then you square the quantity. Squaring that quantity is going to take off the negative signs, allowing us to add up a something that is now positive, always not now negative. So that's our next step, and that's why it says sum of squared deviations from the mean, yi minus y bar squared. In practice, all you're doing is coming over here, taking the value and squaring it. And the way you actually write that down kind of matters. If you write it down this way, -4 squared, you're being fully accurate. This is a positive number, and it would come out as a +16. But now in your calculator, this can become extremely confusing. Let me demonstrate. If I was putting this in the calculator, I wasn't very careful, I might have gone -4. That didn't work. It said answer. So this negative bar doesn't even work if I'm trying to put in a negative number. Anyone see what symbol I actually have to use on the calculator? Yeah, absolutely. Where it has the negative sign in parentheses way down here. That's the actual negative sign we have to use. So let's hit clear and just start over. Now, this one right here. Gotcha. Well, you could use this up arrow as well for exponents. So kind of just depends on how you're putting them in. But the way I'm about to put it in looks good to start. I've got -4, what we're doing here. This is the key I usually use for exponents. If I hit power, then it looks like it went to the exponent position. Power 2 gives me, but after enter, -16. But that's not actually what we wanted. A negative number times a negative number, -4 times -4 is what this is saying, has to come out as positive. Anyone see what went wrong in the calculator? Yeah, absolutely. It still needs parentheses, not just on paper here, also in the calculator. Now, I'm not hyper picky about that. If you forgot parentheses on your paper and you have the right quantity, I think of no harm done. I might just add them in a green pen just as a reminder. But in the calculator, it really does matter. We can get the wrong results just from that tiny, tiny omission. So, I mean, we don't need the calculator, but if this was a nastier number, we would have reached for it, like say -79. So for -4, start with the parenthesis up here above the 8. Throw in the negative sign with that key, not the subtraction key. That's always extremely frustrating. Put in 4, close parentheses, hit your power button, and hit 2. So that will give you what you're expecting, 16. There's another way to square things, just for folks who like another way. Go parenthesis, -4. And this right here, kind of hard to see. Oh, a little bit easier to see on the projector. That's the power 2 button above where it says log for logarithms. And that will just put in that power 2. That's a really common power, so they just built it in. Either way we're seeing it, we're always going to get a positive 16. But that was just a side discussion on the calculator because this can come up in this class. Always try to make a big deal of when parentheses are needed or other algebraic things, just because it can be really frustrating to get the wrong number, even if you know everything about the concept. But let's keep on going through here. We're taking the number to the left, moving it over here and squaring it. Once I get that to work again, there we go. So -2 squared. This will turn into a +4. Next is just a 2. We don't need a parenthesis if it's just a number. If you did put it in a parenthesis, no harm done, but it's usually written this way, 2 squared now. That's also a +4. Last number is going to be 4 squared, or 16. So we have all the square deviations, meaning we have this full entire numerator right here. All of this is now this. And when we go and look at the formula for sample variance, this is the next symbol you see, but that's just a convenient way to say, add up all that stuff. Let's go ahead and use that jargon. Summation yi minus y bar squared is going to be 16 plus 4, which is 20. And then again, so 40 altogether. Haven't had to round just yet, so that's kind of nice. Any questions at all, folks, on getting the numerator portion? Okay, so now for the total formula, here's what we're looking at next. We're ready to say what the sample variance is. Sample variance has the symbol s squared. Sorry for that conflicting color coding there. Should have reviewed how I color code these. Let's stick to green just because it's too late to change. S squared is now going to be that number we just found. What would you all say the denominator should be? It wouldn't be a 1 in this case. It's going to be an n minus 1.
Yeah.
So we need to know the value for n in these data. It is. N is the sample size. And from here, we have n is 4.
Oh,
We kind of zoom out there.
so it would be 4 minutes.
Absolutely. We'll have a value of 3 altogether. Notice that is pretty weird, right? So again, if you're curious about that, I gave an explanation that is kind of just hand wavy. If you delete one piece of data, but you know the mean, you can actually solve for it by just using the formula for the sample mean. So what we say here is there is 3 degrees of freedom in these data, and we divide by 3 to get the most accurate, unbiased sample variance possible. If you want to know more, then definitely take a look at that video there. And if it's optional, so if it just seems like it's,
That one.
yeah, if it seems like it's no good, I like the visuals on it, but the jargon's kind of rough.
That's
Just
why I went
close
back
it
to the
off.
book and I was like, wait.
Gotcha,
But
yeah.
it's fine.
This video is more just targeted about that confusion right there, since that's always really pretty weird. But other questions so far?
I'm gonna figure out the statement step. I'm sure I can go back and watch that and be fine.
Gotcha. Oh, we would just use, we wouldn't get rid of it. Well, by the formula, we have to go the n minus 1. Yeah, so if the n is 4, we could be divided by 3. To me, the safest way to think about it, though, really is whatever you have here, just make it 1 less and you're in good shape. Other questions so far? Okay, well, we just about have the sample variance. It's 40/3, and we have it. I mean, that's the exact value. But in my stats lab, more often than not, you're being asked to round something. It says round your final answers to 1 decimal place. That's the final answers for variance. So it would be 13.3. Let me get rid of this part right here, just so it's not getting too busy. So we have one answer. Y bar is equal 17. I'm going to box these out since there's kind of like a cloud of work that we have on here. Here's the second answer. S squared, that's the variance, came out as 13.3. And the last one, let's get a new color going, is the sample standard deviation. And this one is defined to be just ordinary S. What S does is it takes this quantity and square roots it. Which means this would be equal to the square root of 13.3. Notice I'm using the approximated value. So if you used 40 thirds, your answer is now going to be different. But for a problem like this, where it's done on paper, I'm not too worried about those kind of rounding issues. If I can see what your work looks like and how you did it, then you would get full credit. So I'll go the route of just taking the root of 13.3. That's what the homework is usually going to assume for a multi-step problem like this one. They ask you to round on one answer, they're assuming that you're going to use the rounded value. But the system also checks if you use the exact value. So they're looking for a range of possible right answers. Here, to get the square root of 13, you could do a couple tricks. Here, hit the second key, go back to that power 2 key that we just used, and it produces a square root symbol like that. Put in the value 13.3. And this is the answer that I'll officially state. It's 3.6 for the variance. So altogether, 3.6 on this one. So that's the adventure of doing this kind of stuff by hand. Notice it's tedious, and this was just 4 pieces of data. The data is also rigged. The numbers came out exactly on essentially every step of the way, except for that step and that step. So this is the best case scenario. Yeah, go ahead.
Three considered an intermediate number and not the final answer.
This one right here.
The 13.
Yeah, that's a good question on this one. It's kind of debatable the way I wrote this out. It says round intermediate computations to 3 decimal places. This is the final answer for variance, but it's an intermediate computation for the standard deviation. So I totally agree. If you left it like this, I would give it full credit, but let's go and write out this as just a second alternative. You don't have to change your notes. But if we want it to be as accurate as possible, what we really should have done is taken the square root of either this to 3 decimal places, 13 point, or just the 40 thirds. Let's go with 13.333. This is now following the instructions to the letter, so I kind of like that. Now square root of that thing, same idea. Let's go second key, power 2 key to obtain the square root, 13.333. And our answer is, well, it's going to round to the same place, but it doesn't necessarily always have to. Or hang on. No, thank you for indicating that. This one rounds up. I didn't spot that 5 right there. By the way, that's a nasty way to potentially lose a problem in my stats lab. Sometimes the rounding errors are the worst thing there. So with a more fully accurate answer, it did matter. We get 3.7 in the variance. Let me box that out. So there's our even more accurate answer. Again, the wording on this was vague. I'm going to try to avoid vague instructions like this on a real assignment. But if this was a real quiz, I would accept it either the 3.6 or the 3.7. It's kind of tough to say how the instructions were really intended on this one. Well, any questions at all, folks, with the full process? Okay, just another thought though. For the variance on S squared, when you're doing this in the calculator, everyone's pretty much going 40, divide by 3 for 40 thirds. If you want to do this as fast as possible, you can do another thing. You can go second, square root, and now I want to take this, plug it in there. Shortcut is second. All the way down here, it says A and S, prior answer. And that's just another kind of fast way to get the computation to go without retyping. For me, if I retype something a lot, I'm increasing the probability that I'm making a silly mistake, just keying in something wrong. So those kind of things are more for accuracy, but they also help for speed. But either way we do it, this is the result. Any questions at all, folks, on getting through this one? Okay, let's also review If we decide to not do the table at all, what would we have done? I encourage you to do this essentially for every single problem in this class. Definitely quiz 2. You really want to just use your calculator, so we're not tied up doing this kind of grungy computations, which feels like busy work, really. In our class, we're really just emphasizing the calculator to get all of these values, typically y bar and s. So to get that to go, exactly. This was more just seeing what the formulas are trying to say, see what it looks like by hand. But down the calculator, hit the stat key, hit enter. I still have data from last class in this. Up arrow and the clear button. With the enter, it's going to wipe it all out. So now the data goes 13, 15, 19, 21. With it all put in, hit your stat key once more. Right arrow over to calculate, and then just jam the enter button a bunch of times. Oh, I got it to go twice. And here's our verification. We have a y bar indicated to be 17. S squared is not on here, but we do have SX. That's the standard deviation. Our answer is rounded to 3.7. If we rounded this to 3.7, we would have gotten the same result. So it's kind of nice. That's a good check on our work. Watch out for this one, the sigma as well. This one is not the standard deviation. If you use this value here, what you're assuming is that this is your population. The whole thing you cared about was those 4 observations and nothing else. But in statistics, we're dealing with a sample more often than not. We very rarely have an entire population to deal with. Well, any questions at all, folks, with this problem? Okay, well, we have just one more example on these notes, I think. A couple more examples. We have a lot of measures now for center and the spread of the data, the variability. So I felt like it might be a good idea to just go through this one more time to just try to tie it together. Let's do something at least roughly symmetric. Just some really quick sketches here now that we're more familiar with histograms. So here's my roughly symmetric data. Looks like a slight left skew to it. Something clearly skewed to the left. Sometimes you could get data that looks about like this, just some really gradual staircase pattern going off to the left, definitely left skewed, and something skewed to the right. Sometimes right skewed data just looks like this, maybe even without the outlier. If you saw something that was just that, we have some right skew, add a little bit more, and now it's clearly not symmetric at all, definitely with the outlier. So here, we're just wondering, what would we measure the center with in this situation? I have 2 different colors here. Let me try to get them back in order. One thing that's kind of awful about this version of Microsoft is you can only load 3 pens. I don't know why they're so restrictive on that. The add pen button's just gone. I maybe have to pay more to get it to come back. But I'm restricted to 3 pens if you're wondering why I'm always clicking these around trying to make it work. So this is the best case scenario. If you have data that's at least roughly symmetric, anyone recall what the center should be measured with? Is it the mean y bar or the median m? Y bar would be the mean itself, but the median would be the uppercase M. Yeah, it would be the mean, y bar. A good call. The median does a good job too on this one, M. They're both going to measure about the same position because the symmetry is pretty pronounced on this. The slight left skew just means y bar is slightly moved to the left. Now, once you've picked the sample mean y bar, because you have at least roughly symmetric data, there is now a definite choice for the variability. It cannot be the interquartile range any longer. It must be S. Let's actually give these names just for the sake of getting used to them. Y bar, which is equal to sample mean, and S, which is the sample standard deviation. So if you pick one, say if you decide to use the standard deviation S, then you're using the sample mean to describe the center in this case. Now, that kind of reveals what we're doing in the other cases. If it's skewed, I'm only highlighting skewed here just to signify the direction doesn't matter, left or right skew. For data that's clearly skewed, we wouldn't use Y bar because Y bar is no longer a good measure. It's pulled in the direction of the skew. We use M, which is the median. And we can also say, if we like, M is the 50th percentile. The median is a nice measure of the center because it will always give you a number that cuts your data in half. Half the data is going to be below the median, half the data is going to be above, irregardless of how skewed your data is. It could be the world's most skewed data set. This will still describe the 50th percentile, the center in that way. Here, we would also use M, the median. And now, just like we had a choice that gives us paired statistics, Y bar is always associated with S. Down here, if you're using the median to describe the center of the data, anyone recall what should be here? It wouldn't be mu. Mu would be the, sorry, say again?
Y bar is less than 10.
Not quite on this one. That's a good question or a good statement as well. The sample mean would be less than M on this one because of the left skew.
Oh.
But what we want here is a way to measure variability, how spread out the data is when we're not using the sample mean at all. What other statistic would we have? Good call. That's a tough question. We only calculated it once. We barely looked at it, but that is what it is. IQR. IQR stands for, let's put it down here and just write it out once. Well, it's equal to the third quartile minus the first quartile, and it's called interquartile range. But let's also write down something here. IQR, however you call it, quartile 3 minus quartile 1, or if you call it interquartile range, what this is measuring is the distance covered by the central 50% of the data. So we're looking into the middle. We move left and right until we have the 50% of the data in the middle. The length of that distance is the interquartile range. That's a lot to take in. So my next problem is using these statistics a little bit more so that we have some time understanding those as well. Any questions so far, folks, with our descriptions here? Okay, we also touched on this a little bit, but let's put it here just so it's said once and for all in the notes. Quartile 1 is the 25th percentile. And we say things like percentile a lot in this class. It's always good to come back and remind us, what in the world did we even mean? Any volunteers for a quick description of what does 25th percentile mean? Yeah, go ahead.
So I only know this because I've had babies, but when you have a kid and they measure their percentile.
Very
weight,
important, yeah.
They take your baby's height and they gauge it against 100 other babies born on the same day
Mm-hmm.
and tell you, oh, your baby's 90 percentile in height, 70 percentile in weight.
What if they said 25th percentile in height? What do they really mean
Then
by
they'd
that?
be shorter than most kids there.
Exactly.
They'd be shorter than most kids are born.
Yeah, I think someone was about to say 75%.
Yeah.
Yeah, 75% of the other kids would be taller.
Yeah.
25% of the other kids would be shorter. Not necessarily a bad thing, but that's what we mean by percentile. Then going off to the next one, M. This could be called quartile 2, but essentially nobody does that anymore. We just go with M for median, but it's the 50th percentile. So literally the value in the middle. Finally, quartile 3 is the 75th percentile. So if you're told that your baby is 75th percentile for weight, That's a good thing, I'd say. It means it was heavier than 75% of all the other babies born at that time. It sounds substantial. And that's why this is called the interquartile range. It's taking the 25th percentile. Let me start again. It's taking the 75th percentile, quartile 3, minus the 25th percentile. And that's how we're getting the central 50%. And we're looking at the distance that covers, so we just call it range.
So what is the difference between IQR and range? Because on the homework problem yesterday, there was.
Yeah, we had a bunch.
Range, and there's another one that said IQR.
Gotcha. So the idea with that one is, that's kind of what this example one was all about. It was pretty overwhelming, to be honest. But interquartile range down here refers to what we calculated, the upper quartile minus the lower quartile. But if we just say range and nothing else, that means we're taking the maximum observation minus the minimum. In other words, we're going from here, the minimum, all the way to the maximum and saying, what is that distance, the whole range of the data?
So if there's an outlier, like an extreme outlier, is the range going to differ extremely from the IQR than it would in that problem?
It would, yeah. Yeah, it absolutely
And it
would.
makes that
Let me see if I
very
have an outlier
different.
somewhere. Yeah, like in this case, the range would go from 16 minus 2, so it'd be a distance of 14. But the interquartile range on this one is probably going to be pretty short, about that distance. So the more extreme your outliers, your range gets more and more unstable because it's always the maximum minus the minimum. So it's almost involving outliers every single time they occur. But the interquartile range, it's more stable. Just like the median is stable against outliers, so is the first quartile and the third quartile. So no matter how skewed your data gets, this is the better range to say how spread out your data is. It's not influenced by the outliers like the other statistic up here.
The mean is affected by the outliers, or the median is affected?
The median is not.
Median.
Sorry about that. I must have misspoke. Yeah, the median here is not affected by outliers much. But the sample mean is, it's always pulled in the direction of skew, so outliers would pull it as well. Lots of information to take in all at once. Any other questions about the range or interquartile range? Okay, well, let's take a look at where we're at. Down here on the notes, this is the tie together of all that kind of stuff. And to put it into action, here's our last problem for these notes. After this, we'll start taking a look at chapter 3. So it says here, the 2015, that's already turning into old data, wow, Urban Mobility Scorecard, this was done by the Texas A&M Transportation Institute, included data on the estimated cost of millions of dollars resulting from traffic congestion for different urban areas in 2017. That's kind of confusing. The 2015 Urban Mobility Scorecard is about 2017 data. Weird naming convention, but let's keep on going with it. Must have been something along those lines. They say next, the following data are for the 13 largest urban areas that had a population over 3 million. So these are the largest urban areas. New York, Los Angeles is definitely up there. I would have thought San Diego, there's big cities. But yeah, San Francisco at least made it on there. San Diego's humongous. But these are the 15 largest, as it was in either 2017 or 15. I'm not too sure. This is foggy right up. But when we see this, that's the data. We look at, for example, Houston, Texas, $5 million means that is the estimated cost of millions of dollars resulting from traffic congestion. So let's highlight that just to say that's essentially what all those numbers are saying there. So Houston is experiencing a $5 million loss in, I guess, revenue for the city. That's probably what they're mentioning here, resulting from traffic congestion. So if we take all those 13 cities, notice the 13 right here is a sample size, but these data are a lot different than other data we've seen when it was a real world context. In this one case, let's put here and say, this is not a random sample. And that's important. If it's not a random sample, then any conclusions we make about these data do not apply to urban areas over 3 million. Because we looked at strictly the 15 largest. This is not representative of every urban area with population over 3 million. So the results here do not generalize to anything. It will only be relevant to the 13 areas here and nothing else. But we took all these values. If we were to ask computer software to make a histogram, here's what it would look like. It says a histogram of these data are provided below. Describe the shape of this distribution and which summary statistic best describes the center and variability. So starting with shape, would you all agree that we're looking at unimodal in this case? Absolutely. So this is the main peak. These are outliers that are not enough to cause bimodal in the data. So we'll say unimodal to start. Absolutely, good call. Due to this portion of the histogram trails off to the right, so we have right skew data. Yeah, absolutely. I would say the outliers are these. These two right here are just what you would typically see for right skew data trailing off. But once you have a decent gap and there's still data far to the right, these are the ones that we're considering to be outliers. And we'll say 2 outliers on the upper end. You might say between 12 and 16. Anything you can do to describe where they're at is great. I'm not too picky on that. So if you just told me there's 2 outliers, I would accept that as well. But it's good to say where as well, I'd say. So I usually do that. Well, any questions, folks, with the description of the shape? Okay, I try not to ask these kinds of questions. There's too much going on in part B. I usually break this up into a part B, but here we are. There's 2 questions in part A. What would you say is the best summary statistic to describe the center? Say again? Absolutely. For the center, we must use the median, M. And that's only because the data happened to be skewed. So if it was nice and symmetric, we would have used sample mean, Y bar instead. So that describes the center, but we also want variability. Think of the word variability as being synonymous with spread. That's not how you spell spread. Let me try again. Okay, so for spread or variability, once we decided on using the median, M, we don't have any choice over here. What's the statistic that we must use? Absolutely, it'd be the interquartile range, IQR. So let's go IQR. And because that's a heck of a simple and an interesting concept, let's write it down one more time. Interquartile range. So we know what statistics best describe these data, all because of the skew. Now, part B just asks us calculate, and interpret the values of the median interquartile range. That tells us we're on the right track with using those. But we want to interpret them using the context of this study. So this is the challenge in statistics sometimes. It's not as hard to get the values in the calculator and crank them out. This would be about our 5th or 6th time doing it. What is hard is interpreting them, even harder, using the context as you go. So let's take our time with that. First step, got to get the data in. And to me, this is hard data to actually put in with all these repeats. You have to be really careful with that. So first step, hit stat, enter. And if you just have 4 pieces of data, you might be tempted to hit the delete key. I often do that. That works just fine. Now next, 15, 13, 7. Now we have 2 5s, 5 and 5, and thank you, 5 4s, 1, 2, 3, 4, 5 of them. It's good to be methodical with this kind of thing. Thank you, 3 threes. 1, 2, 3 of them. And yeah, that looks good. It says L114. We're stopping because we had 13 pieces of data. We up arrow, it says that's your 13th piece. So with all that put in, hit your stat key, right arrow, and jam the enter key. So here's the data. We don't want anything on this page because our statistics we're using is median interquartile range. So just hit the down arrow, it reveals more statistics. Awesome, let's go. N equals 4, we'll come back to the interpretation of that one. And we also need interquartile range. Good call. The calculator doesn't directly give it, it gives the actual quartiles. But like you said, it's quartile 3, so 6, minus quartile 1 to 3.5. So 6 minus 3.5 would give us 2.5. And we did the first part, getting just the statistics out. Now we'll go really carefully with the interpretation. But any questions first, folks, on getting either of those two numbers? Okay, now if you're interpreting what you've got, one thing that helps a huge amount is look at those numbers again, the 4 and the 2.5. Anyone see what the actual unit is associated to those numbers? Exactly. So here we have $4 million, and the 2.5 is $2.5 million. So let's do the interpretations next. To really get a nail on that, the kind of process with the statistical problem is you read it once. Anything you notice could go in a formula. We've pretty much just been indicating n, try to write it down. But then as you go through the problem, good idea to read it again. So let's do that next. Sometimes with all these different word problems, and sometimes they're pretty long, it just becomes a lot to keep in your head all at once. So coming back to the problem helps out a humongous degree. So when we said $4 million, we were measuring the 50th percentile for estimated cost resulting from traffic congestion in, let's see, for different urban areas. It was for specifically this, the 13 largest urban areas with a population over 3 million. So for this one, if we were going to interpret it, we might say the 50th percentile of 50th percentile of what? It would be this right here. Cost. Yeah, we could say the cost then of the 13th largest. So we'll say, sorry, say again. Yeah, pretty much, absolutely. The 50th percentile of cost from traffic congestion. And then as you said, it's not for every city, it's for the 13 largest urban areas. But again, one thing we don't want to have to do is just copy the whole problem each time we say it. If you abbreviate this a little bit, that's completely fine and expected as well. So we could say the 50th percentile of cost of traffic congestion for these 13 urban areas. Now, if we say these 13 urban areas, we're talking about this. It brings us right back into the full context. So you're always welcome to abbreviate. You shouldn't feel like you were writing down every single detail in the problem each and every time. Just allow enough of a hook, 13 urban areas, to refer to the total context, and you're in great shape. Absolutely, yeah, that would be referring to these as well. So anything that refers to anything in the problem, some way, somehow, to me, you're using the context. Again, if it feels like you're writing down the whole problem a bunch of times, that's just busy work, really, not actually the spirit of the problem. It's just making sure you're talking about what's happening in the problem some way. and you're welcome to abbreviate. It's kind of expected that you will. So let's finish off this sentence. The 50th percentile from traffic congestion for these 13 urban areas is $4 million. It's debatable if it's faster to write $4 million or just write down the number with a dollar sign. So up to you. So that one's not too bad. Does it make sense on how we got that interpretation? Okay. Now this one's tougher in my opinion. I'm personally not a fan of interpreting the IQR because the sentence you write just seems weird. But the idea of it is it's the distance covered by the central 50% of the data. So we just have to say that statement, tie in the context. So coming back down, we'll say for the IQR here, the range of the central 50% of these urban areas is $2.5 million. And notice I did, in fact, leave something off on the context for this one. I didn't say anywhere right here, the range of the central 50% of these urban areas is $2.5 million for the estimated cost due to traffic congestion. If you left it off here, but you said it somewhere else, I'd say that's just fine as well. These statistics are paired together. You mentioned the context once already here. If you leave some off down here or left off all the context and just said the range of the central 50% of these data is 2.5 million, I'd say you still have a great response. Yeah, go ahead.
Well, they give like a quote, so like that's their quote, so it's a range from between $2.5 million to $4 million to like fix something, like if it's like fix the issue.
Oh, what do you mean by the quote? Sorry.
Like if someone were to fix the problem of the traffic congestion, and if they were giving them a quote for the money.
I see. Yeah,
You know,
the
and-
amount of money to
Is that
redo
how
their
it's
highways.
So like the central would be like, okay, it's gonna be the low cost. I don't know.
Well, I think I like what you're saying here. If we looked at some graphics where we put it in IQR, say right over here, it's saying if you're looking at the typical cities, the ones in the middle where it's all clumping, on the lower end, you're losing, I think it was this one, $3.5 million, up to the upper end, $6 million. That's telling you that's where all of the central 50% of your data is going to lie from that value to that value.
So could that sentence count as an answer?
Absolutely.
Coming in between $3.5 million to $6 million.
I would like that, yeah. And honestly, I think it's the better answer because,
In terms of
yeah, the IQR just gives you one number. You're losing information, and that's a real side effect. So if you gave me the actual bounds from where to where, that'd be a great way to write as well. So that'd be perfect. I think that when you do these problems in my stat lab, however, they're usually going for an interpretation that just refers to the one single number. So that's kind of unfortunate. But in your work, if you're mentioning the IQR or just the components, quartile 3 and quartile 1, I definitely would say that's a really great response. Well, any other questions, folks, with this one here? Okay, well, we did it, folks. This is the conclusion of chapter 2. I ended up taking a lot of extra days on this one, but I'd say chapter 2 is pivotal. There is a lot of things going on here, so it was well worth our time. Let's save this. Any last questions whatsoever on chapter 2? Okay, one question you might have is, well, this is a lot of stuff. How do I study for chapter 2? We do have an upcoming exam down here on this week, Monday, September 16th. There'll be review documents here where you can just look at practice problems like we've been seeing and study. But honestly, another way, if you want to get going right now, go here. All these problems are probably going to feel a little bit fresh because we haven't seen them in quite some time. You open it up to chapter 1 notes. This is now a worksheet. solve these problems. Some of them, like example one, this was a problem where we're just introducing the course. This is not a great one to solve. But things like, say, example two, this gets you started on reviewing the whole entire course. And then you could just look at what did we do in the class from the chapter one notes right here, and you get a check on working out those problems. So the blank lecture notes altogether, I mean, those are great problems. My exams are based off those notes right there, which are what the quizzes are also based off of. So this is a great source. And I'll have others again. I'll have documents I created as well as problems in the book as well for folks that like to read the book as well as you're studying. Well, with 2.5 done, let's now take a look at chapter 3. Again, that's one is a short one. And we have a good 15 minutes to work through it. Let's take a look at where we're at here. I still want a calculator, so let me put this over here to get started. So chapter 3 says relationships between categorical variables. So essentially what this is saying is in chapter 3, since we're only looking at sections 3.1, 3.2 on these notes, we are looking at 2 categorical variables. What things can we say? What things can we learn about the data when we're handling 2 variables at once? In other words, is the idea behind these notes here. Once we get to chapter 5, we're going to change it up and say 2 quantitative variables. How can we analyze that kind of data? What can we say with what we have? But here's where we'll start first. 2 categorical. There's a lot of stuff to talk about here. And the way I did these notes was I made one humongous example that hits the different things that you'll see in the homework. Again, it's a pretty short section, but lots of different pieces of terminology. Let's give this a start, maybe go through part A. We'll see where we end up and potentially do part B, but I don't want to get too far on these notes. We only have about 13 minutes and some change. And this is not a nice problem to break in half across a weekend. So let's give it just a short start, and we'll come back to this one on Monday, doing the major parts. Starting off, it says, study from the University of Texas Southwest Medical Center. So that sounds pretty serious. Examined whether the risk of hepatitis C was related to whether people had tattoos and where they got their tattoos. By the way, hepatitis C, I think that's the bad one. This one is going to attack your liver. You could become terminal from this condition. So it's really very serious data, once again. They say we have data from 626 participants of this study, which is summarized into a contingency table. So sample size here is 626. That word is definitely new. When you hear contingency table, that just means we're displaying counts, perhaps percentages, of one variable against another. So there's really 2 categorical variables we're dealing with here.
Can you do this one more time? You compare them against what?
Yeah, in the contingency table, what we're doing is we're taking 2 categorical variables and comparing them against each other. How do the counts line up for one variable and another simultaneously? So say, for example, when you're looking at this table, if I circle any one of the cells in the main body of the table, by the main body of the table, I mean not looking at the column totals down here, nor the row totals going here. If you circle one of the numbers on the middle here, it tells you something about both of those variables. So for example, this 53 is saying that out of the 626 participants in the study, exactly 53 of them had tattoos, but they weren't done at a parlor. Maybe they bought a home tattoo kit off Amazon, something like that. Who knows? Maybe they went to prison. Could be anything. They have a tattoo not done in a parlor. And at the same time, they do not have hepatitis C. So that's the typical way we read the table. Does that make sense to folks at the moment? Okay. So looking at this, it says describe the individuals. Let's start right there. The individuals is just really asking us about the sample.
Whether they have hepatitis C or not.
Absolutely, but it's more trickier than that as well because it also includes people that didn't have tattoos. So we have to say everything all together. That's probably where I would start too. We could say, what are the individuals? What do we know about these people? Well, yeah, there are, or let's say the individuals are the 626 people, or you could say participants in the study. I went with people only because I want to emphasize they're human. And if you say people, you're probably talking about humans, not objects. So that's the best we can do on that one. Kind of uncomfortable, right? We'd like to say a little bit more, but that's all we have. We can't even say healthy people necessarily because, I mean, some of them have a serious condition. 47 of them have hepatitis C if we're looking at this column total right here. And they had hepatitis C from different sources. 17 at a tattoo parlor, 8 at a home tattoo kit or something like that. 22 people with hepatitis C and no tattoos whatsoever. So that's the best we can really say. And sometimes we're just forced to do this uncomfortable problem. I don't know a lot about the individuals. All I know is that they are those 626 people selected for the study. So weird problem there. But this one's getting back into some interesting things. I put around here variables with the option of plural, but it's definitely plural because if we're dealing with the contingency table, that means we have 2 or more categorical variables that we're dealing with. So what would you say the first categorical variable is? Absolutely. Let's say the variables are, we can say tattoo. And if you like, you could say tattoo parlor, tattoo elsewhere, none. But usually if you're indicating a categorical variable, you just give one overall name. The name is going to be tattoo. It's categorical. And it didn't ask us to describe the categories, but if we were, we would say the categories are those 3 right there. Let's just say it as a way to think about the variable. It's categorical with categories, tattoo, and the parlor, tattoo, elsewhere, and none. I really didn't think ahead and give myself enough space there, so let's just insert some. So they are tattoo, that's one of them. And we need a name for the other variable. Any volunteers for naming our second categorical variable? Yeah, absolutely. So one way you could abbreviate that is just say hepatitis C. But again, this is just a stylistic choice I'm making. If you on the first variable said tattoo parlor or tattoos elsewhere or none, you're naming the categorical variable. And over here, if instead of saying hepatitis C, you said having hepatitis C or not having hepatitis C, that works as well. You're naming the categorical variable in the same way. But typically the way the categorical variable is named is just one quick word, if we can make it one quick word, as the overall description. If you just call this hepatitis and nothing else, then that would have been just fine for the categorical variable's name. Think of categorical variables as things like, say, gender, eye color, blood type. Usually you wouldn't say too much more than that. The more than that would be the actual categories. So let's say here for hepatitis C is categorical with, this seems kind of strange, to call a variable categorical and list out its categories. It almost seems like circular in the way we're describing things. So if you don't like that, you could say hepatitis C is categorical with outcomes. Hep C, no hepatitis C. I'll abbreviate that to just hep for hepatitis. So those are the variables of this actual study. Now what we want to do is analyze these variables, and we want to address this question. is hepatitis C related to whether people had tattoos and where they got them? The most important word is this word. We're looking for relationship, but we're not looking for a cause and effect type of relationship. In fact, that's impossible in this study. If we want to see if tattoos cause hepatitis C or hepatitis C cause tattoos, those both of them sound kind of strange. The way they would have had to done the study was gather 626 participants, split them into 3 groups by random allotment. One group will have a tattoo done in a parlor, one group will have tattoos done elsewhere, none, follow them for some time and just see who gets hepatitis C or not. That's an experimental design that just sounds insane, right? It's got huge ethics problems. It could never be run. The government would never fund it. You would have to be kind of an evil sounding person to run that kind of study. Some questions like these, cause and effect is essentially unknowable, yet we still want to find information. Yet, when we say related, we have to make sure our conclusions are not saying cause and effect in any kind of way. There's probably another variable that could be associated how people are getting hepatitis C and how it's related to getting tattoos or not. But this is a good stopping point for us, I'd say. Before we get to the marginal distributions, the marginal distributions will take us some time to describe and get through. So this is where the study will end. But if you're really curious if there's a relationship or not, I'll leave this last part right here. It comes down to this kind of graph. So if you look at that, no hepatitis C is in orange, and notice how the category changes. It gets bigger and bigger as you move across the categories. That is an indication of some relationship. Well, not necessarily, because we don't know if they're cause and effect, but there's a higher chance that you would have it. Well, yeah, I can see what you said was correct. Yeah, sorry, I got a little turned around in my head. Absolutely. So if you're at a tattoo.
If you get tattooed in the parlor, you
Well,
might have a higher chance of getting it.
Well, actually, looking at that again, no hepatitis C. Yeah, hepatitis C is very large, so it's the highest chance that it just goes down, just like you said. Absolutely. So that shows it is a relationship. If the bar here looked exactly the same over here and over here, we would have said no relationship whatsoever. And that's interesting in its own right. But we'll break through this problem and see what everything else is going on Monday's class. Any last questions or comments then, folks? Okay, have a great weekend, folks. We're done with week 3, so I think that's like 13 more to go. Almost there.
Not even close.
Yeah.
Going over chapter 2, and that helped a lot. So,
Awesome, glad to hear that.
yeah.
Thanks.
I think my dad, my favorite homework system as a go. Yeah, you get understand in a moment. I still haven't had a pin for it, so by tomorrow, they'll figure it out.
Supposedly, we'll see if they are able to do that or not.
Should be, I think.
Any questions?
Yeah, how long, you said that we're gonna have extra time other than tomorrow to do the quiz, how long do we have?
I don't actually have any late policy whatsoever. So if you don't get it done by the due date, all that really happens is I put in a score of 0, but the moment you get it back into me, I'll put in the updated score. Yep, you bet.
When I see my books. I like your face.
Awesome, thank you.
And then I accidentally, when I was clearing my last data, I accidentally deleted L1.
Oh, I can bring that back for you. Let me pull this up to show how that goes. So to get show L1 back. Clear this first. What you want to do is hit stat
Okay,
and keep down to option 5.
okay.
Enter a couple times and something happened. Now go back to stat and enter, and you should see your L1
Oh.
coming back.
Yeah, perfect.
Awesome. That
Thank you.
Cool. Yeah,
Would the square root of whatever the fraction is be an acceptable answer on an exam?
that'd be a perfectly fine answer. I would take that.
Okay.
Yeah, absolutely. You bet.
It's the bits and bytes for infographics. We have Jack Bradley. Thank you. Hello, Brad.
Thank you.
Is it
Yep,
for-
have a good one.
You did.
What class? Near the data information to, yeah, whatever, I'll pay that. I am not. I struggle with that class. I currently am. I struggle because I really suck with computers. That's all the computer jargon, I like call it. Yes. It was it's killing my passion for writing this class student. So that class wasn't too bad. Cause you just work on one paper the whole semester. Yeah. But we have a bunch of time. Thank you.
Yep, have a good weekend.
I don't remember, I don't think it's this class. I have a doctor's appointment in a couple of weeks.
Hmm.
I don't think I'll be late to this class. So I'm gonna. On a Tuesday.
Gotcha. If you end up not making it in, you can always come back to
Oh, it's Tuesday.
the recorded lectures on our Moodle page.
I'll be here. I'll be on the class.
Well, that's right. It's Monday, Wednesday,
So
Thursday.
it's not
Yeah,
this class. Yeah, I was like, I don't think it's this class.
I'm still learning my schedule.
But I was like, I gotta make sure that I'm.
Hello.